Hi, we are Team 26088, and our project focuses on bio-inspired mineral recovery from mining wastewater. Mining operations generate large volumes of wastewater that contain dissolved metals. Traditionally, this water is treated as waste. However, many of these dissolved metals are actually valuable. So instead of simply removing contaminants, our goal is to recover those metals while also improving water quality, creating both environmental and economic benefits. We'll start by introducing the problem and current treatment methods. Then, we'll explain our bio-inspired design and modeling approach. After that, we'll go through our results, including performance, energy use, and economic analysis. Finally, we'll cover over safety considerations, environmental impacts, future improvements, and conclude with key takeaways.
Mining operations produce large volumes of wastewater and tailings that contain dissolved metals like copper, nickel, and cobalt. These metals are valuable, but they're typically not recovered because most systems are designed for disposal, not recovery. This leads to environmental concerns as metals can contaminate ecosystems and economic losses due to the disposal of valuable resources. We based our design on data from the Morenci copper mine to reflect realistic, large-scale conditions.
Our objective is to design a system that recovers valuable metals from mining wastewater while also treating the water for reuse. We take a bio-inspired approach to improve separation efficiency, reduce environmental impact, and generate useful outputs. These outputs include a metal-rich product stream, reusable water, and solid materials that can potentially be repurposed. Currently, mining wastewater is treated primarily through neutralization. In this process, metals are precipitated out and stored in tailings facilities. While this removes contaminants from the water, it doesn't recover the metals in a useful form. As a result, valuable materials are lost, and long-term storage creates environmental risks. There are several major challenges with current systems. Mining wastewater often contains dissolved heavy metals that can contaminate both surface and groundwater if not properly treated. Tailings storage requires large containment areas and carries risks of leaks or failure over time. Additionally, valuable metals are lost instead of recovered, creating both economic and resource inefficiencies. Because of these issues, there is increasing pressure to develop solutions that combine water treatment with resource recovery. Biological systems are capable of performing highly complex processes from chemical synthesis to shaping entire environments, often with remarkable efficiency. These efficiencies can rival or even exceed traditional engineering systems. Because of this, researchers are increasingly turning to bio-inspired designs. These approaches not only improve performance, but also tend to be more sustainable, biodegradable, and cost-effective compared to fully synthetic solutions.
Our process uses TanFloc, a natural coagulant made from plant-based tannins. It acts as a polymer that binds dissolved metal ions, allowing us to recover valuable metals instead of losing them as waste. Under certain pH conditions, the functional groups on TanFloc become negatively charged, allowing positively charged metal ions to bind. TanFloc works across a wide range of pH conditions, making it flexible for different treatment stages. It also forms large, dense particles that settle quickly, improving separation efficiency and reducing processing time. Another key advantage is that TanFloc is biodegradable, making it a more sustainable alternative to traditional coagulants like alum or ferric salts.
Our design is based on a flow rate of approximately 3,500 gallons per minute, representing large-scale mining operations. We use mass balances to check metal recovery, size reactors based on residence time, and incorporated parallel units to handle high flow rates. Key assumptions include steady-state operation, complete mixing in reactors, and typical industrial equipment performance. These assumptions allow us to model the system realistically while keeping calculations manageable. This process flow diagram shows our full-scale system. It integrates multiple reaction and separation steps designed to efficiently recover metals from mining wastewater. Each unit plays a role in either preparing the water, capturing metals, or refining the final product. We divided the process into several key phases. First, large solids are removed with a filter screen to protect downstream equipment. Next, we raise the pH using limestone, which causes metals like iron and aluminum to precipitate and be removed. Then, TanFloc is added in a reactor. Controlled mixing allows it to bind remaining dissolved metals into larger flocks that can be easily separated. This step is where we achieve the majority of our metal recovery.
In Phase 3, the metal-loaded TanFloc is settled and sent to a filter press. The separated water is returned to the mine with improved quality, making it suitable for reuse. In the final phase, we add sulfuric acid to release the captured metals into solution, producing a metal-rich stream. The remaining tan flock is filtered again and recycled back into the system. To evaluate performance, we used Visual Mintech, a water chemistry modeling tool. We based our inputs on real data from the Morenci mine and adjusted conditions to reflect our process. The model shows that increasing pH removes most iron and aluminum, while tan flock effectively captures metals like copper, nickel, and cobalt. Overall, the results confirm that our process can achieve strong removal and recovery under realistic conditions. For more complex parts of the system, especially with recycle streams, we used additional hand calculations. Our results show recovery of over 90% of copper, 26% of cobalt, and 47% of nickel. In terms of product quality, the final stream is about 40% metals by mass, compared to roughly 2% in the original wastewater. This represents a significant improvement in both recovery and value.
Our total energy demand is about 13,000 kilowatt hours per day. This corresponds to roughly $480,000 per year. Mixing accounts for the largest proportion due to the size of the reactors. However, energy only makes up about 0.35% of total operating costs, meaning it is not the primary economic driver.
Our economic analysis reflects a large, realistic system design. We found that costs are now primarily driven by chemicals like limestone and sulfuric acid, while energy makes up only about 0.35% of operating costs. The capital cost is around $172 million, with operating costs about $137.7 million per year and revenue of roughly $143 million per year. Overall, the process is close to being economically viable, but profitability depends on reducing chemical usage and improving recovery efficiency.
Compared to earlier designs, this version reduces energy usage but increases chemical costs. As a result, the overall economics are now driven more by reagent use than by energy consumption. This highlights the importance of optimizing chemical usage moving forward.
Safety was a key consideration in our design. We're working with chemicals like sulfuric acid, so proper handling, storage, and PPE are essential. On the process side, large reactors and high flow rates introduce risks like spills or equipment failure, which we address with monitoring systems, containment, and routine maintenance. We also consider economic risk since the process depends on chemical costs and metal recovery performance, which can impact overall feasibility.
While our process is more sustainable than traditional methods, it still has environmental impacts due to its large scale. Most of this comes from construction materials like concrete and steel, as well as energy use. These impacts could be reduced by incorporating renewable energy sources like solar. Using biodegradable tan flock also helps reduce long-term environmental risk from spills.
Future improvements focus on reducing chemical usage, increasing metal recovery efficiency, and optimizing the overall process design. These changes would improve both economic performance and sustainability.
In conclusion, our process is technically feasible and offers clear environmental benefits by enabling water reuse and recovering valuable metals. The main limitation is economic, driven by primarily chemical costs. With further optimization, this system has strong potential to support more sustainable and resource-efficient mining operations.